Okay, folks, this is chapter 7. We're still in section 7-1. This is recording number 2. All right, where we left off was talking about the interval estimate, okay? And I think the most important thing that I want to share with you is that the interval estimate is used because we have no way of knowing how close a particular point estimate is to the population mean. So we don't have any way of knowing that, so it just makes sense to use an interval estimate. And the interval estimate of a parameter is some interval, and it is used to estimate the parameter. This may strike you as strange, but this estimate may or may not contain the value of the parameter that is being estimated. We don't know, okay? All we can do is come up with a confidence level, and we'll talk about confidence levels in a few moments, but we don't know for certain. The way we write the interval estimate, the way we write it is we say the parameter is specified as being between two values. So an interval estimate for the average age of all the students, okay, remember the average age was 22.7. I beg your pardon. The average age was 22.3. So it's 22.3 plus or minus 0.4. So add 0.4 to 22.3 and you get this. Subtract 0.4 from 22.3 and you get this. So we can say it either way. We can say it's 22.3 plus or minus 0.4, or we can write it like this. All right, so as the author says, the interval may or may not contain the parameter. A degree of confidence, and then usually we use a percent to explain what our confidence level is. A degree of confidence must be assigned before an interval estimate is made. Okay, so what does this mean? The degree of confidence must be assigned before an interval estimate is made. So what you do is you decide ahead of time. You say, well, I want to be 95% confident, or I want to be 96% confidence, whatever you want, okay? So you decide ahead of time how confident you want to be. Now there's trade-offs. If you're more confident, then there's some trade-offs for that. We'll see that here in a little bit. Okay. Well, actually, it's right here. If you want to be more confident, okay, so let's say 95% is not good enough. You want to be 99% confident. Well, then the interval is going to be larger. It's going to be a bigger interval. So that's the trade-off. Sometimes if you make the interval too large, it becomes almost pointless, right? I mean, if you said, well, the confidence interval for the mean age of college students, let's see, what's he saying? 99%, okay, is going to be 22.3 plus or minus 0.6, whereas before is 22.3 plus or minus 0.4. So you see what's going on here is the 22.3, that's measured, that's the 100 kids that you measured. So that is the point estimate. So it's the point estimate plus or minus what is commonly referred to as the margin of error. So if your confidence level is higher, if you're more confident, if you're 99% confident, this margin of error is going to get bigger, because what you're trying to do is you're trying to say, hey, I'm going to make the interval larger so that I am more certain that the true value, the true mu, is inside of that interval. Okay, so a confidence interval, the confidence level of an interval estimate is a probability. So we know what probability means now. It's the probability that the interval estimate will contain the parameter, assuming that a large number of samples are selected and that the estimation process on the same parameter is repeated. So what he's saying is, listen, if you did this experiment, if you took 100 kids out of Riverside Community College District, if you took 100 of these kids over and over and over, you kept selecting 100 kids, what we would expect is that the parameter of the mu, the mean of the population, is going to be in that interval, okay? So we have two concepts here. We have the confidence level. Confidence level is how certain are you? So you would say, well, I'm 95% confident. So that's my confidence level. I'm 95% confident that I have the correct confidence interval. So here's the confidence interval. That's a specific interval estimate of a parameter. And you determine that by using data obtained from a sample and by using the confidence level that you desired for the estimate. So do you see what's going on here? You pick this first. You say, well, I want to be 95% confident. Well, if you want to be 95% confident, that's going to dictate, that will determine what the confidence interval is going to be. So the ones that we typically use is 90%, 95%, and 99%. Okay. So we'll show you how to do this later, or the book will show you how to do this later, okay? But let's just have a little intuitive explanation first, okay? All right. So the central limit theorem says that when the sample size is large, approximately 95% of the sample means of the same size will fall within 1.96 standard errors of the population. In other words, mu plus 1.96 times this standard error. Where the heck does that come from? And let me be more precise. What it's saying is, if you're looking at these X bars, right, the sample means of same size samples, so those are the X bars, and you've taken these samples from the population, they're all the same size, those X bars, okay, those X bars will fall within plus or minus 1.96 standard errors of the population mean. And then those are the words. Here's the mathematical symbols. What it's saying is that mu plus or minus 1.96 times this will give you, is an interval that will give you 95% of the X bars. So if you pick a specific sample mean, if you pick a particular X bar, there's a 95% probability that this interval, mu plus or minus this, will contain X bar. So likewise, there's a 95% probability that the interval specified by the same thing, this is the same interval here, will contain mu, and we'll show that later. But he's trying to give you this intuition saying, hey, look at these X bars, they're just random variables. We know how the random variable X bar is going to be distributed. We have a theorem for that. It's called the central limit theorem. So a particular X bar is going to be within this interval, mu plus or minus 1.96 times this so-called standard error is going to be in there, and that's because of the central limit theorem. And remember, the central limit theorem says that certain things, okay, and as a consequence, this statement must be true. And I'll show you that in just 1 second here. Okay, so where does this 1.96 come from? Where does this come from? 1.96. Well, that's obtained from the table that we were using before that dealt with the standard normal distribution, this so-called Z-score. So let me bounce back to that, and I hope I can convince you of that. Give me 1 second here. Okay. So back here, this is from the textbook, the PDF version, so it might be a tiny bit different from the book. Okay, so the central limit theorem says that the X bars have a certain shape. What's the shape? It's a normal distribution. What's the mean? It's mu. What's the standard deviation? It's this sigma, that's the standard deviation of the population, divided by the square root of n. So how do we get the Z-score? Boom, there it is. Okay, this is what we talked about when we were in the central limit theorem. Okay, it's normally distributed. So this is what it looks like. Here's my cartoon. Here's my mu. 34, let's just round it off. 34% will be to the right, 34% will be to the left of how much? Mu plus 1 sigma sub x bar. they call this a standard error. It'll be within 1 standard error of mu. Okay, so what would you say when you look at this? What you say is, hey, I don't know. Give me an X bar. I pick an X bar. All right. I don't know exactly where it is, but there's a 34 plus 34. That's what, 68 and some change, 68% and some change probability that it's going to be inside here. Okay. How about within 2 standard errors? Okay, see, here's the boundary. Within 2 standard errors is going to be, let's just round everything off. 13 plus 34 is 47. 47 plus 47 is what, 94%? So 94%, probably closer to 95%. Let's say 95% is going to be in here. Okay, right in here, 95%. Well, maybe I don't want to be so, so casual. Maybe I want to find out, well, what is the real number? Well, the real number, if I want to say I want to be exactly 95%, instead of being mu plus 1 times the standard error, mu plus 2 times the standard error, what I do is exactly what I did before, and I multiply by the appropriate z value in order to get exactly what I want. Okay, so let's take a look at that. Give me 1 second here. Okay, so this is table E in the back of your book, the cumulative standard normal distribution. So remember, we have this cartoon down here that tells us what these guys in here, what does that represent? It represents the area to the left of a particular z value. So 1.96, here's 1.9, then I come over here to 0.6. Boom, there I am, 1.96. What it's saying is it's 0.9750. 0.9750 is to the left. So what is that telling me? That means that there's let's put it in percentages. So it's 97.5% is to the left. Okay, so if 97.5% is to the left, that means that 0.250 is to the right percent. Okay, I don't have any way of writing that on the screen here. You're just going to have to write that down yourself. Okay, so 1.96 z-score, a z-score of 1.96 tells me that it's 97.5% is to the left. So if 97.5% is to the left, then write it out on a piece of paper. What that's telling you is that 2.5% is to the right. Well, if 2.5% is to the right of this z number, this is that z-score, come over here to negative z. 2.5% is to the left of negative 1.96. That all comes from this cartoon here, and that's why when we were talking about this cartoon, I kind of urge you to make sure you look at the cartoon and draw those cartoons. So what's the bottom line here? The bottom line here is that if you select a sample mean, select an X bar, okay, it's going to be a 95% probability that it's somewhere in this interval, mu plus or minus 1.96 times the standard error. Okay, so you're 95% confident that the population, or I'm sorry, you're 95% confident that the X bar is going to be up there. Well, it can be shown that the population mean is also within that same interval. And this is just an intuitive way of saying that, hey, this makes sense. It's just using the central limit theorem and the z-scores. Okay. All right. Okay, so let's think back. I had that cartoon a moment ago, okay? I had the cartoon. So I'm wrong 2.5% over here, and I'm wrong 2.5% over here. So what that's telling me is that I have an error budget. I am wrong 2.5% on the right, 2.5% on the left. I'm wrong 5% of the time. We call that alpha. The alpha is how much error are you allowed. So alpha represents the total area in both tails, the right-hand side and the left-hand side. So half of it is on the right, half of it is on the left. This z sub alpha over 2 represents that number that we need to get that particular alpha on both sides, okay? So that gives us this formula, and we'll talk about that in the next tape.